In this video, I want to share an interesting property of floating point numbers that I learned while going through one of the questions in this book here, Computer Systems, a Programmer's Perspective. I've been going through this book because, I started as a programmer, so I think this book has been a good introduction to, well, computer systems so far. So what I'm going to share is actually triggered in that sense by a practice problem in the book, and there is this problem right over here, and that is about the relative precision of floating point numbers. The question, or rather the practice question is as follows: for floating point format with k-bit exponent and n-bit fraction, give a formula for the smallest positive integer that cannot be represented exactly because it would require n plus 1 bit fraction to be exact. And the answer is right over here. I give the answer because what I'm trying to do is not to work through how to get the answer, but I think how the process of understanding the answer has led me to better understand, this property, which is relative precision of floating point, which I think is very interesting, which I'll talk a little bit more at the end. So for n equals to 23, which is usually a 32-bit floating point number. So in a 32-bit, that's very thick. In a 32-bit floating point number, um, oh, that's too thin. 32-bit. You have the sign bit, so S, you have 1 bit, you have k-bit exponent that is 8 bits, and you have the n-bit fraction, which is 23. That gives 32. So the question in particular uses a 32-bit floating point in the IEEE 754 specification, but this applies to, well, any floating bit representation following the specification, um, even though the specification only specifies for certain number of bits. Regardless, we are going to talk about 32-bit. So let me explain how I came to understand this answer. So when the question talks about representing positive integers exactly in the floating point format, we are talking well, whole numbers here. So we want to find the smallest positive number that the floating point format using 32-bit floating point, the smallest number that 32-bit floating point cannot represent. So I am going to start with how I understand floating point and how this has shown me why this number here is the smallest number that F32 cannot represent. If we take a floating point representation, so we are going to ignore the sign bit, but regardless, we still write it here. Then we have, let me shift it down. So you have the sign bit here. Then you have 2, 3, 4, 5, 6. You have K here, and you have N over here. The way I've come to understand floating point is, and specifically positive floating point, but I think it extends to negative floating point numbers as well, is we can divide up the representation of floating point numbers into groups. And this also ties into the property that of positive floating point numbers that um, computers can do comparison operations greater than, less than, or floating point with the same circuitry as unsigned integers, for example, right? Because floating point representation, positive ones, are such that the size increments also follow a standard bit representation of an unsigned integer, in that the numbers, or rather the bit places at the right of the floating point number, represent smaller increases in the value compared to bit places further to the left. I hope that makes sense. So when I say divide it into groups, what I'm talking about is, if we take a look at, let's say, normalized floating point numbers, right? So for normalized floating point numbers, you have an exponent, which is derived from k, right? Which is k minus the bias. Well, in this case, the exponent is actually k here. So I'm going to change this to yeah, that works. I'm going to change this to E and this to K, just to match the question a little bit better. And there is an M value here called the mantissa, which is 1 plus the fraction. If you want more details on how this works, you can check out my previous video. I actually talked a little bit about how floating points are represented. So when I talk about groups, the value of a floating point is derived from 2 to the power of k times the mantissa, right? So the groups are essentially powers of k. If we take the smallest value of k for for a normalized number, that is 1. And for a floating point 32, I believe the bias is 127. Let me check real quick. Yeah, the bias is 127. So k, the smallest value is minus 127, which equals to negative 126. So the first group of normalized numbers that can be represented in a floating point is actually 2 to the negative 126 times multiplied by the fraction. And when we think about the fraction in this sense and why this is a group, I don't really need to talk about what the value of the fraction is, but because the fraction is essentially an increasing range of numbers from 1 to 2, right? Because every bit, because the fraction is essentially um, the numerator over the denominator, where the numerator is determined by the bits in n. I mean, the fraction is determined by the bits in n, and how that's determined, you can check my previous video for that, but it's essentially a value from 1 to 2, right? And why it's 1 is because of the mantissa. We have a leading 1 over here. So every bit increment, similar to how unsigned integers increase the lowest bit by 1, the value increases by 1. when you multiply it by a constant, we get a constant increase of the value of the floating point number. In essence, that means whenever we increase the exponent by 1, the value of e rather, which yes increases the value of the exponent k by 1, this goes to 2 is to the power of minus 125, and so on and so forth until you get 2 to the power of let's use 23 in this case, right? And because the value of the fraction is actually let's use f, sure, over 2 to the power of 23. Yeah, so when you have this, yeah, so this is just to showcase the different groups, right? So this is how it goes on and on. For each increment in the exponent k, the 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 relative precision actually increases according to the power of um, the exponent. So perhaps to use a relatively simpler example, let's say our fraction is just 1 over 2. So every increment in uh, the value of n here is just, well, it's 1 over 2 or 2 over 2. I guess it's only 2 values. Let's use 1 over 4 instead. So if we have 2 to the power of 1, right? Then maybe have 2 to the power of 2, and let's have 2 to the power of 0. So every increment here of the fraction, when you go from 1 over 4 to 2 over 4 to 3 over 4, the value here, because this is it's a different color just to show calculations. That's because 2 to the power of 0 is 1, right? So 1 times 1 over 4, every increment of the fraction is just an increment in the value of 1 quarter. For 2 to the power of 1, it is 2 times 1 quarter, which means every increment in the value of the fraction is an increment of half. And I think you can see where this is going. This is 2 to the power of 2, which is, well, it's actually, which means every increment here, it's an increment of 1. And if we just use one more example, this is 8 times 1 over 4, which is 2, right? So every increment in the fraction is an increment of 2. Okay, it's not visible. Yeah, it's every increment is an increment of 2. So it works the same for our 32-bit floating point number over here, whereby at 2 to the 23, right, every increment in the fraction, because these two numbers essentially cancel out, right? So every increment in the fraction is an increment of 1. So when f is 2 to the 23 minus 1, that is the largest value that can be represented when the exponent k is 23. when we add 1 to the value, because the value of n here is all ones, the value of n will increment by 1, so it will become all zeros. And the value of the exponent will bump up by 1 as well, which means it's 2 to the power of 24. And this is essentially 1 over 2 to the 23. Right? And if we cancel this out, this is essentially 2 2 to the 23. Yeah, so I was confused for a bit, but I think I got it figured out. So when the exponent jumps up to 24, here, the value of the fraction n and the mantissa here is 0, while the mantissa will be 1. So m here is 1, which means the next value, 2 to the power of 24, can still be represented exactly, because 2 to the power of 24 multiplied by 1 is, well, 2 to the power of 24. Now, when we increment the next bit, the next fraction bit, so let's say this becomes 1, right? The mantissa value becomes 1 plus 1 over 2 to the power of 23, right? And so let's write it down. 2 to the power of 24 times 1 plus 2, no, plus 1 over 2 to the power of 23, which is 2 to the 24 plus 2 to the 24 over 2 to the 23, which is 2 to the 24 plus 2 of 1. Yeah, math. It's been a while. But yeah, as you can see, when we increment the smallest fraction bit by 1, that means this value here becomes, the last bit becomes 1. The next, the smallest value of the number jumps by 2. We went from 2 to the 24 here, right? This is just 2 to the 24 times 1, which is 2 to the 24. The next value is 2 to the 24 plus 2, which comes back to the question here, where the answer is 2 to the power of n minus 1, where n in this case is 23, and even n in this case here is 2. So 2 to the power of 2 is, rather 2 to the power of 3 is 8 plus 1, 9. And the same concepts apply here because the increment in the smallest fraction bit is 2 instead of 1. So 2 to the power of 3, you get, if this fraction value is 0, you get 8, which you still can represent exactly. But if you increment here by 1, this is 8 to, let's just write this down. So this is 8 times 1 plus 8 times 8 times 1. Let's write out the whole thing to the power of 3 times 1. What am I doing? 3 times 1 plus 1 over 4. So this is 3, which is 8. Sorry, this is not times, plus. So this is 8. 8 plus, sorry, not equals to 2, but this is 2, 1, so equals to 8 plus 2. And so going back to the same formula here, 2 to the power of n plus 1, where in this case n is 2, so 2 to the power of 3 is 8, plus 1, 9. 9 can't be represented exactly because the next increment is actually 10. And I think this is interesting because if we extend this example further, right? Let's say we use this. Is this the correct one? Let's say we use this over here, right? This equation, and we increment the power, right? 2 to the 25 times 1 plus 1 over 2 to the 23. You get 225 plus 2 over 223, which if you simplify, is plus 2 squared, which is 4. So that means every increment in the fraction where the exponent k is 25 is an increment of 4. And this brings me back to relative precision of floating point numbers. And I think this is the interesting property that I wanted to share, and also how it works in floating point because of how the representation is. And what I've come to, or what has been quite a bit of a revelation for me, is that perhaps I've not really yet understood how this relative precision might be more useful, perhaps in certain industries, certain um, calculations, because I've always thought that, exact precision is all that matters. That means using things like unsigned 32, signed 32-bit numbers, then you have the 64-bit equivalents, so on and so forth. But those numbers are precise within a much, much smaller range. And of course, there are whole numbers, but if you want decimals, you can, just shift it around and manipulate the values by multiples of 10 accordingly. But floating point is unique in that the precision, and I do note here that I'm talking about normalized numbers only, normalized floating point numbers, the precision scales with the value of the number. At smaller values, the precision is much higher, while at larger values, as we can see in these few examples over here, right? The precision scales with the size of the number at much larger numbers. Just for some context, 2 to the 24 is actually 2 to the 24 is this value here, which is pretty large, right? And if the precision from 2 to the 24 to 2 to the 25, which is like, I don't know, 35 million plus. I'm not going to calculate that. But within this range, a precision of plus minus 2, I could see why it's acceptable for some industries and calculations. And I think that is the interesting revelation that I wanted to share. That I learned from just this question, and uh, how I came to the understanding of how the relative precision of floating point works. So I hope that was interesting for you. It was certainly very interesting for me to struggle through this question and to try and understand why the property of the floating point value is as such in terms of the relative precision. I struggle to explain because I think this is what I'm trying to do, which is to show that in learning there will be struggles, and when I share these concepts, what I learn about these concepts with you, there is that struggle there. And when I share it, I understand it better. And by sharing it with you, I hope you see that, struggling is normal, struggling is fine. And I hope you can learn something from this as well. Um, I'll be continuing to make my way through this book, Computer Systems, CS, APP, as well as some other stuff that I'm reading. I think particularly the Art of Unix programming right now has been very interesting so far. Just at the start, first chapter, but I'm enjoying the read so far. So if you enjoy this kind of video, I'll be sharing more about things that I learned in my journey, interesting things that I find. Perhaps I might talk about Art of Unix programming uh, in a future video. And if that's the kind of content that you like, do like and subscribe so that you can be notified of the future videos. That's all. Thank you. Take care.